So let me talk about this example here. This is secondary carbocation. We just kind of similar things that we just started. You look at the secondary carbocation forms. The question is whether rearrangement happens or not. Then you need to look around and see if there's an adjacent carbon has a more higher substitutions. And then yes, this secondary carbocation, the carbon with two just carbon chain attached to that. But adjacent carbon having a 1, 2, 3 carbon. So if you have this hydrogen move, then you are forming more substituted tertiary carbocation, which is better than secondary carbocation. So I imagine this will happen. So this definitely makes sense, this rearrangement happens. But you can also see that there's another hydrogen there, right? So I mean, let's use another example here. What I'm trying to say is, this is a tertiary carbocation. Does this carbocation will move to the adjacent position? So we can probably do the similar thing. This is adjacent carbon having a hydrogen there. If this hydrogen moves to positions, right, then you're going to get the carbocation move to that carbon. It's going to be this. That is a tertiary carbocation. There's a secondary carbocation. So tertiary carbocation becoming a secondary carbocation is actually starting with this carbon trying to looking for more trouble, right? They don't want to be getting more unstable. Tertiary carbocation is already better than the secondary. I mean, it's kind of it's bad, but it's somewhat tolerable. Why do they have to move the hydrogen and becomes more terrible? Right? So that's why this doesn't happen. So you're gonna look these type of things, trying to figure out whether rearrangement happens or not. If they becomes better, they will move. If they becomes worse, they will not move. Right? It's all based on energy. Will this happen? This hydrogen on this carbon move over there, then you are moving the carbocation to the primary positions. And that is also not happening because the primary is even worse than secondary. So it's all based on energy. So you kind of get the idea, right? Adjacent carbons are more substituted, and then you can make a more substituted carbocation than what you're starting from. Then yes, you have to expect a rearrangement. If you move the hydrogen from the adjacent carbon and it becomes less substituted, it will not happen. The question is this one, like this. And this is a pretty simple one. Let's say you make a carbocation from this carbon. You know this is a secondary carbocation having a 2 carbon substituted. Will this carbocation move? Then what would you say? So you have to look for the possibility of if there's a more substituted carbon in adjacent side. And this carbon having a 1, 2, 3 carbon substituted. So if this hydrogen move, make a hydrogen, and you are forming a tertiary carbocation, so which means a secondary becomes a tertiary, which makes it way better. So rearrangement will happen. But what about this? Will this rearrange? I mean, one way you can think about it is, this is a secondary carbocation only having a 2 carbon. Let's say if we move this hydrogen over there, then you are making another secondary carbocation, and then you got the adjacent hydrogens that can move further. It makes a tertiary carbocation. So it can be eventually becomes a tertiary carbocation. We know this happens. If you start from that, this happens. The question is, how many times can we expect this happening? It can keep happening over and over again. So that means a carbocation relation is a little bit further away, but if you move this hydrogen, carbocation will move there. If you move that one, eventually go there, and then really that's where it stops. And the correct answer is no. Initial thing, you're making a secondary carbocation becomes another secondary carbocation. And I'm telling you, moving hydrogen is not a simple feat for this molecule. It's actually requiring a huge amount of energy. They're in agony. They have to use that whatever the leftover energy to make the hydrogen move, hoping that it can get better. But if it ends up being the same, then what's the point of moving the hydrogen? So it doesn't happen. I mean, if this happens, then anywhere you get the carbocation form, it eventually goes there. And of course, it can happen at a very high temperature. There's a lot of things happening. Like when you get the petroleum from the, pump it from the ground, they go through the refinery, just sorting out what kind of chemicals in there. But not only that, they are huge high pressures and the heat can make the things moving around. So the cracking process, you can form a lot of different things. But in normal circumstances, it doesn't happen. So they don't really look, they don't really move more than one carbon. Maybe that could happen with the elevated temperatures and elevated pressures, but in a regular situation, they don't become another same substituted products. Even though once this happens, maybe this can be better, but this first step, it basically is a deal breaker. They don't move for that. In a way, they kind of don't, right? If they do this, they can get there. But just one immediate step is what they're looking for. So I've been telling you, carbocation can be arranged from less substituted from the more substituted, only for that reason. They don't want to get less substituted. They don't want to get same substituted, right? They only move if there's a chance to be more substituted. So that's kind of a rule we are building up right now. So keep that in mind and tell me if this carbocation will move or not. So what I'm telling you here, this is the carbon having a 3 carbon substituents. So this carbocation is called tertiary carbocation. If you remember that, tertiary carbocation is pretty stable already, right? Primary, secondary, tertiary. That's the end. There's no way you can get quaternary because quaternary carbocation doesn't exist. So it's the top of the list. So it's already stable. So these shouldn't move at all. And then if you look at the adjacent side, that's a primary carbon. That's a primary carbon. There's no way it's going to abandon such a happy position and then going for the terrible end, and then it becomes a primary carbocation. What about this side? That if this hydrogen move from there, it's going to be making secondary carbocation, right? And then we just talked about they don't demote themselves going down to secondary from the tertiary. So you should say this doesn't happen because the tertiary carbocation is more substituted than secondary carbocation in normal circumstances. But in this case, they will rearrange happily. They becomes a secondary carbocation from the tertiary carbocation, which is contradicting what I told you earlier. But there's a reason why this happens here. Why this happens here? Because this is a secondary carbocation, but not the ordinary secondary carbocation. This is a resonance stabilized secondary carbocation. Right?